Alright students, so in this video we're going to be going over vibrational spectroscopy, and specifically we're going to be talking about IR spectroscopy or infrared spectroscopy and its selection rules. So keep in mind that we said in the last video that infrared spectroscopy is a direct absorbance method. So the electron absorbs the infrared light, which enables it to excite from one vibrational state to a higher vibrational state within the same electronic state, right? So we had this lovely picture, right? Both of our vibrational levels are within the same electronic state. There's no other electronic state involved when we're doing infrared spectroscopy, because infrared light is low energy. All right, so if we think back to one of the videos from Monday, we talked about if a transition occurs or is allowed in a particular type of spectroscopy, it must have a transition dipole moment that is not equal to zero, but that is greater than zero. And so our transition dipole moment, the other day we wrote it as mu12. Here, since we're talking about vibrations, we know that our ground vibrational state is 0. So while we could write initial and final, 1 and 2, here we're just going to go ahead and make that switch to 0, 1. So we're going to say this is mu01, which would then be the integral over all space of psi 1 star, mu z hat acting on psi 0, and mu z hat is that transition dipole operator. So by convention, remember when we were talking about molecular orbitals, the bond was always along the z-axis. We're going to carry that convention over in spectroscopy and define the bond of interest as being along the z-axis. Really, our axes and our coordinate system is sort of arbitrary, but we are going to set this such that it is always defined as the z-axis along the bond of interest. So if we're thinking about a harmonic oscillator, then we're going to be thinking about taking the integral from negative infinity to infinity. Because z is the axis of our bond and the axis we care about, we're going to say that both of our harmonic oscillator wave functions, psi 1 star and psi 0, are functions of z instead of functions of x. So we're making that variable change from x to z simply because we're defining that bonding axis as being along the z-axis. So we're using our harmonic oscillator wave functions. And we know our bounds. So now the question is, what is mu z hat? What is this transition dipole operator for infrared spectroscopy? So our transition dipole operator is going to change depending on what type of spectroscopy we're doing. But for infrared spectroscopy specifically, mu z hat has the following form. The first term is mu0, which is simply the dipole of the operator, the resting dipole or the equilibrium dipole. Our second term is the change in dipole with respect to z, so this partial derivative of mu with respect to z, evaluated at z equals 0. So that's what that subscript 0 means. It means evaluated at z equals 0 times z. And this, if we were to continue, we could write an infinite number of terms, and this would become a Taylor expansion or a Taylor series of our dipole moment with respect to z. So we're expanding it in z. And this is, again, the transition dipole moment operator for infrared spectroscopy only. So typically, when we're thinking about infrared, we only deal with these first two terms, although in some cases it becomes important to deal with the third and fourth terms. For right now, for one-dimensional infrared spectroscopy, we only need the first two terms. So let's go ahead and plug those in and see what happens. So mu01, that first term, mu0, is just a constant, so we can actually pull it all the way out of the integral. So we'll have, for the first term, mu0 times the integral from negative infinity to positive infinity of psi 1 star psi 0, where psi 1 star and psi 0 are simply our harmonic oscillator wave functions, dz. Our second term, when we take the partial derivative of mu with respect to z and evaluate it at 0, it becomes a number because it's already been evaluated. So we can actually pull that out. It's been evaluated times the integral from negative infinity to positive infinity of psi 1 star z psi 0 dz. And again, if we need our further terms, then we would continue in the same manner. So what do we know about the harmonic oscillator wave functions? Can we simplify this in any way? So we know that our harmonic oscillator wave functions are orthogonal and normalized, but the orthogonal part is important because that means when we do psi 1 star psi 0, because those two wave functions are orthogonal to one another, that integral is going to go to 0. So this first term goes to 0. It doesn't matter. So in fact, the transition dipole moment depends solely on the second term, which doesn't go to 0 because of that extra z inside of the integral. So mu01 is this change in dipole moment with respect to z, evaluated at z equals 0, times this integral, which looks a lot like an average position integral. All right, what this means is in order for mu01 to be something other than 0, there must be a change in the dipole as the molecule vibrates, right? So mu01 being greater than 0 means there must be a change in dipole throughout that vibrational motion occurring. And so that's actually our first IR selection rule, is that we have to have a change in the dipole as the molecule vibrates. And in fact, the more change in the dipole, the larger the IR peak for that transition will be, right? So IR peaks, their probability or their size is actually mu01 squared. And mu01 is directly proportional to that change in dipole moment. We have one additional infrared rule, which we will not derive, we'll simply state, and that's that the change in quantum number nu has to equal plus or minus 1. So we'll see transitions like 0 to 1, 1 to 2, 2 to 1, 3 to 2, but we wouldn't see a transition of 0 to 4. This is going to be a highly improbable transition. That's not to say that those never occur. In fact, in the lab that we do next week, we will see that they do sometimes occur, but they're less likely, they're less probable. All right, so let's work through one example, thinking about the fact that delta nu is always equal to plus or minus 1, and that we must have a change in dipole as the molecule vibrates. So all of our motions will have a set of quantum numbers, right? So they'll have possible transitions where the delta nu would only be 1. But in order for those to be possible, any transition to be possible, we need there to be a change in dipole moment as the motion happens. So we're going to look at the example of carbon dioxide, which was an example we used when introducing FTIR spectroscopy several weeks ago in lab. So we're going to use carbon dioxide. So as you might recall, we said that the number of vibrational modes for a linear molecule is 3 times the number of atoms minus 5. And the number of vibrational modes for a nonlinear molecule is 3n minus 6. So how many vibrational modes should carbon dioxide have? Carbon dioxide should have 4 because it is a linear molecule with 3 atoms. So we have 3 times 3 minus 5, or 4 vibrational modes. So one of its vibrational modes is the symmetric stretch. So if we think about symmetric stretch here, the symmetric stretch looks as if you put a mirror on the central atom. And so everything is moving either closer into the central atom or further away from the central atom synchronously. So in this case of carbon dioxide, this might look like both the oxygens compressing in towards carbon together, or both of the oxygens expanding away from carbon together. And if we think about the dipole moment in each of these cases, in both of these cases, oxygen is more electronegative than carbon and is thus pulling electron density towards itself, but in an equal and opposite fashion as the opposite oxygen. And so in both of these cases, there's no net dipole. And so these are not going to be allowed in IR spectroscopy, or these might be called IR inactive modes. Or this mode would be called an IR inactive mode. I guess that would be singular, huh? All right, so another type of stretching motion or vibrational motion would be the asymmetric stretch. And so in this case, this would mean one of the oxygens is compressing in towards the carbon while the other oxygen stretches away. And we could think about those oxygens switching roles. If we think about the dipole moment here in each of these cases, we'll start with the picture on the left. We can think about both of these. In both these cases, the oxygen is pulling electron density towards itself, but because those oxygens sit different distances away from the carbon, they don't balance one another out. So there's a net dipole in one direction, and there will be a net dipole in the opposite direction when it swings the other way. So as we think about this vibrational motion occurring, the net dipole is going to be going left, right, right? It's going to be switching back and forth. So there is a change in dipole moment throughout this vibrational motion. And because this dipole changes as the vibration happens, this is an IR allowed or an IR active mode or motion. Another motion that carbon dioxide can have is the in-plane bending mode. So here we might think about carbon sitting still and the two oxygens bending up away from the carbon or bending back down also away from the carbon and towards one another. So you can think about them sort of like a bird flapping its wings maybe, right? So the oxygen would be the wings. All right. So here if we think about the dipole for each of these cases, again, we'll start on the left. The oxygens are the same distance away from carbon, and they're both pulling equally on carbon's electrons. However, they're no longer 180 degrees apart from one another. They're no longer pulling in opposition. And so there's a small net dipole in the left-hand side going up towards the oxygens. And on the right-hand side, this net dipole is going to be coming down, again, towards the oxygens. And so as the vibration occurs, the dipole is flipping back and forth between up and pointing down. And so this is also allowed or an IR active motion. Another example of a motion that CO2 can have is an out-of-plane bending mode. And so this would be like if we took our picture from the one above, the in-plane bending, and rotated it 90 degrees towards you. So now the oxygens are either bending out of the screen towards you or into the screen further away from you. And as they bend forwards and backwards, you'll have a change in the net dipole moment also going forwards and backwards, forwards and backwards. And so again, you're going to have this being allowed in IR spectroscopy. So this is also going to be an IR active mode. All right, so think about what questions you have in practice. Remember that WebMO can help show you these motions as well as tell you how allowed something is in IR spectroscopy. That was actually one of the columns in your table in your WebMO results. So practice this, think about a few molecules, see if you can work through what's happening in your head before moving on to Raman spectroscopy selection rules.